Okay, so now we're gonna try to create an algorithm based on the model that we've created, and what we'll do is basically look at the diagram that we came up with, think about the different classes or agents that we have, and the different events that can happen, and then see if we can actually come up with some rules of how we would put this into a computer. So recall we have a model where we're going to have three classes of individuals: susceptibles, they can get infected, they're currently infected, and can pass the virus, and recovers, they've cleared their infection, and now they're pretty much out of the game. And two things can happen: transmission, an I infects an S, who then the S will become another I, and recovery, an I can recover and become an R. So that's kind of summarized in the diagram, and now we're going to try to think about each of the different processes that can happen, and how we can actually make some rules to put those into a computer. For that, we need to think a little more about how we want to model this, and we've been talking about the who, the what. Now we're going to talk about the how. How are we going to incorporate these processes? And I think just to make things easier, I think these the I's becoming R's, or the infected's recovering, it's an easier process to think about. So let's start with that one, with the right side of the diagram, and think about that. So we're going to come up with some rough justification of how we could actually model those. So let's start with some rules. So we're going to think that anyone who's currently infected can move or recover and jump into the R compartment or box. The more people there are in the I class, then the more transitions we should see, right? If no one is in the I class, we should not see people moving from I to R, because there isn't anyone in the I class. On the other side, if there's lots of people in the I class, then maybe we should see a lot of people recovering at any given day, right? And we're going to use day as our unit of time. So just to give you some intuition, let's assume that the recovery rate is about 10% per day. So 10% of the people who are infected at any given day will recover on that day. So we're going to make the parameter 10% and think about that as something to help us. So a question is, okay, on average, how many people should then recover on any given day? Right, so maybe we can just quickly argue about that with the screen. And so we say, if today, at the beginning of the day, there are I numbers of infected, let's say that that's 1,000. And we say that R is 10%, right? So 10% of those 1,000 individuals should recover. That's the amount of people that we should see recovering on that given day. Well, then how many people should recover? Well, it should be I, the number that I have, times R, which is the 10%. Oops. And then 10% of 1,000 in this particular case ends up being 100. Right? So on a given day, when I have 1,000 people infected, if the recovery rate is about 10% per day, then I should see about 100 people recovering on that given day. So that's written there in the bullet, right? The main point, the main thing that we should think about is, well, then that tells me that the number of people I should be seeing getting recovered every day should be my rate, in this case, times the number of people that I have, or R times I. So if I go back to the pen, then really this is the key feature I want to see, right? That the amount of people who are getting recovered every day should be the product, in this case, of the rate times the amount of people that actually have infected and who can get recovered. Now, for the next side of things, the people getting infected, that's a little bit trickier. We'll try just to articulate how we're going to actually do it. And because then it's not only a fraction of or a function of how many people we have in S, right? Because it should also depend on how many people we have in the I compartment. If no one is infected, if no one is infectious, then no one should go from the S to the I, right? There's no virus, there's no people who can transmit, right? So the amount of people who go from S to I should be a function of both how many people I have in S and also how many people I have in I. And that's where we actually get to make or some assumptions and do what we call math modeling, right? We need to come up with some rules of how these things are going to occur. So in the slide, you can see that some things that we need to care about. For an infection to occur, an S must be an I. And once they meet, then the transmission can occur. But not everyone, not all the time that you meet someone with flu, you're going to get the flu, right? There has to be some conditions. The person has to sneeze or actually expel some virus out of their body, and then to actually go and you have to breathe it in or touch it and put it inside your mouth or some ways. So not every time that you meet an eye, you're going to get sick, right? So let's say that every time you meet an eye, the probability that you're going to get infected, it's P, right? And we're going to use that parameter. Now, unless we model explicit contacts and we do something more sophisticated for people who are moving around, then we need to come up with a way to count all the possible ways that S's can meet with I's. So we'll do that next. So what we're going to do is just that in the end, all the possible connections that can happen, well, it's going to be a function of how many S people I have and how many I people I have. And in the end, what I can think about is that the total possible number of connections or contacts that could happen, well, it should be the amount of people I have in S times the amount of people I have in I, right? The more I have in I, the more I have in S, the more potential contacts I'm going to have. But of course, not everyone is going to meet everybody, right? You don't see everyone who has the flu. You don't see everyone in your town. You just see a small proportion of them. So maybe then we can have another parameter that we're going to call C, which is the rate at which people meet each other. All right? So we're going to then multiply those all potential number of contacts, S times I, times a rate of contact, what we call C, right? And once a contact occurs, then with certain probability, we're going to actually have a transmission, right? So how many infections should we see every given day that starts with S susceptibles and I infecteds? So if there are C times S times I contacts, then we can say, but the probability that there is an infection when there is a contact is P, then on average, we should see, as we see here in wrote in the slide, C times P times S times I infections a day. So going back to our model, if that is how many infections we're going to see per day, then we see that for our B that we had in our diagram, is actually in this case the product of those two parameters, the rate at which people meet each other times the probability that if an S meets an I, actually an infection happens, right? And although I'm going really fast through this, and I encourage you to go back and look at the slides, review the things that we're saying, in the end, we've already come up with all the ingredients that we need to build a computational algorithm to simulate fluid transmission using this model. So let's articulate how that algorithm is going to look at and actually summarize it. So, of course, for us to be able to put in a computer, we need to tell it, the computer, what the values of my parameters are going to be. So we're going to need to pick values for my parameter B and my parameter R. Understanding that B is the rate of infections per S times I potential pairs that are in the model, and that R is the recovery per individual. We also need to start somewhere, so we're going to have to come up with, okay, if I have a population of 100,000 or 10,000 or 1,000,000, then I need to decide how many of those are going to be susceptible to begin with, how many infecteds I'm going to start with, and how many people who are already recovered. So it makes sense that, for instance, we would make the susceptible maybe n or n minus 1. Then maybe I start with 1 infected, 1 person that comes with the infection, and then 0 recovered. And then once I have my initial conditions, then I can go and say, okay, what are the things that can happen every day? Well, people can get infected, and then infecteds can get recovered. So how many people can get infected? Well, if there are S susceptibles and I infecteds, we said B times S times I is the new people that I should have infected every day on average. So what I can do is, well, start with my S's and I's at the beginning of the day, and at the end of the day, I can update my number of infecteds by having whatever I had plus B times S times I, which is the number of new infecteds that I'm going to get. Now, if S's become infected, they're not S's anymore. So I also need to update the number of S's that I have and then reduce what I started with at the beginning of the day by the number of people who got infected. So this number of new people who get infected, then I can just go ahead and add it to the I's and subtract it from the S's. It's a zero-sum game. So if you gain infected, you're losing susceptibles. What is the other thing that can happen? Well, people can recover. The infected can recover. So we said, how many people do I expect to recover every day? Well, if R is the rate of recovery, well, it should be R times I. So then the number of R's that I should have at the end of the day should be what I started with plus the new recoveries that I have. And then again, it's a zero-sum game. If someone recovers from the I to the R, then the I should decrease by that same amount. So if I clean this now, this is now the algorithm that we can actually enter into a computer, right? Every day, update the number of new S's, I's, and R's given these rules. So this is an example of a computational algorithm that we can use to simulate the model that we have created to simulate the propagation of the flu in a population. The WEF tool that I showed you earlier, it uses pretty much a similar algorithm with some differences. Here we're modeling things, or we talked about maybe doing algorithm jumping one day at a time. The one that's actually in the tool is a continuous time algorithm. So it uses something that's called differential equations. So it's a little more detailed, but not by much. And if you don't know what differential equations are, you will learn that at some point. And then you'll be able to actually code a model such like that and actually write those equations that govern how the dynamics happen. If you are curious about it, you could actually, in the tool, just go to the developer tools in your browser, and you can actually see the equations and the algorithm that is running behind the scenes. That's one of the cool things. These tools allow you to make explicit and see exactly what's behind the scenes running those or producing those outputs and those curves. We'll now move to trying to expand that model and maybe add one more component, which is the one that we're missing, which is vaccination.